Today we are going to solve the problems on balancing of rotating masses. In the last class, we have studied about the balancing of rotating masses in single mass by a single mass on the same plane and single mass balancing by different masses on different planes. Okay, based on that, we have taken up the relation between the balancing masses and disturbing masses by analytical method and graphical method. Today, we are going to solve the problems on the single mass rotating, and it is balanced by different masses and single mass. Then let us consider a problem. There are four masses M1, M2, M3, M4 or 200 kg, 300 kg, 240 and 260 kg respectively, and the corresponding radii of rotation are 0.2 meter, 0.15 meter, 0.25 and 0.3 meter respectively, and the angles between the successive masses are 45, 75 and 135. So find the positions and magnitudes of the balancing masses which are to be required if the radii of rotation is 0.2 meter. So finally, from the given data, we have collected that we are having the four masses with the some radius of rotations. We need to find the balancing mass. How much of mass will be required to balance the all four masses which are rotating at the radius of rotation which are given in the question itself. But in the question, it was clearly mentioned that we need to find the balancing mass, but it is rotating at a radius of rotation 0.2. So we need to get a solution for the balancing mass which is rotating at a radius of rotation 0.2, and also the position, that means with respect to horizontal or corresponding to the four masses, how much of the angle of position is to be placed for the balancing of these four masses. So write down the given data that M1, M2, M3, M4 and the corresponding radii of rotations R1, R2, R3, R4 and theta also given, but you just read the question carefully that the angles between successive masses, that means the angle of the first mass and the second mass and the second to third to fourth as given. So we have to clearly make a diagram. So the angular position diagram is to be done very carefully. And in the question, it has given the radii of rotation. That means finally this balancing mass radius is 0.2 meter. And what is the magnitude means? That means the mass we will calculate. So firstly, we have to draw the question in the angular position diagram. Since we know the values of M and R, we can directly calculate the centrifugal forces. So we know the formula for centrifugal force, that is M omega square R. But for all the cases is the omega, that means the speed of rotation is same, so we can eliminate the omega value. So finally centrifugal force for the first ball is M1 R1 equal to mass 200 into R is 0.2 meter. So finally we get it the centrifugal forces for all the four masses or four balls which are of 40 kg meter and 45 kg meter, 60 kg meter and 75 kg meter. Then draw the angular position diagram. This is the very important diagram to positionate the final balancing mass and disturbing mass also. Then let us draw a horizontal line. For every problem, you just make a reference that either we can draw the any mass of the ball as a reference, or directly we can take a some x or y axis as a reference. So here, based on the given data, there is a relation between successive masses. So 1 to 2 is 45, 2 to 3 is 75, 3 to 4 is 135. But what is the position of the one with respect to the reference? So there was no angle of that. So let us consider the first ball mass as a reference according to position at the remaining three masses. So here I am taking the first ball mass, that means the 200 kg mass as a reference. So it is to be kept on a reference, that means x-axis. So point out O and draw a horizontal with a radius of rotation as 0.2 meter. Here we have to consider that a proportionate scale is to be required. So accordingly we have to position the angle or length. So take a reference 0.2 meter. That means we can calculate it as 2 centimeters for our consideration. Okay, for our scale value, draw a 2 centimeters of line and make a ball shape which is of 200 kg, and then that is the reference, that is the first mass, and take up the position of second mass as 45 angle with the radius of rotation as 0.15 meter. That means 15, that means 1.5 centimeters is enough. We have taken up the scale as 0.2 meter as 22 centimeters. So we have to proportionate the same angle to all the values also. So here it is a 0.15 meter, that we will call it as a 1.5 centimeter. There you have to make an angle of 45 degrees and a position with the 300 kg, and from there, that is second mass to third mass, angle is 75 degrees. So from the reference, that means from the origin, it is an angle of 75 plus 45, that is 120 degrees. So from the origin or from the reference, it is 120 degrees. From the second mass to third mass, it is a 75 degrees. Whatever may be the angle of reference, we can put up our according to our reference or the successive masses also. Then the 75 degrees is placed, and there with a length of 0.25 meters as 2.5 centimeters, and make the position of another ball, that is 240 kg, that is M3, and whatever the remaining last mass is M4, which is positioned at 135 degrees from the third mass. So from the reference, how much of angle is up to there 120, from after there 135. So totally it is 255 angle. From the reference we have to kept 120 255 degrees centigrade and make the position of the last mass, which is of 260 kg, with a radius of rotation 0.3 meters as 3 centimeter. Okay, firstly we have to construct the angular position diagram. So if you draw the angular position diagram correctly, then the position of balancing masses will be placed in the right position without any disturbance. Then we have collected the centrifugal forces M1 R1, M2 R2, M3 R3, M4 R4. Then for solving the problem, we have learned two methods. One is analytical method and the second one is graphical method. The analytical method is related with sigma h and sigma y. That means horizontal components and vertical components. Then by solving with analytical method, this angular position diagram is as follows. We have already constructed the angular position diagram or space diagram. Then resolving the M1 R1, M2 R2, that means centrifugal forces horizontally and vertically. Okay, sigma h means cos theta, sigma v means sin theta. So multiply all the values, M1 R1 cos theta 1, M2 R2 cos theta 2, M3 R3 cos theta 3, M4 R4 cos theta 4. But we have to remember that here the theta angle will be equivalent to the position of all the masses with respect to the reference only, not be in the successive. So be careful while putting the angles that here the theta is positioned with respect to the reference. Here the reference for the mass 1, that is which is called a reference. So the angle is theta is 0. Then what about the theta 2? It is positioned about 45 degrees. Okay, if you see in the diagram clearly, we have positioned all the values of angle with respect to reference only. But in the question, they have given the angles that for the successive masses. So whatever may be the positions it has given in the question, we have to convert them into our reference plane only. Then only we can solve the problem in the correct manner. Then cos theta 1 plus uh, cos theta 1 means that is the reference 0 degrees, and next angle is 45 degrees, 45 degrees, and cos theta 3 in the question 2 to 3 it is 2 to 3 it is 75 degrees, but the 45 and the 75 will go for the 120 degrees. So like that we have to position that. So finally sigma h as 21.6 kg meter. So for solving the problems in balancing of rotating masses and reciprocating masses, we have to be calculated with the calculator only. Don't give the values by approximately or guessing. And then now solving the vertically M1 R1 sin theta 1. With the same theta values, we have to position with sin theta. Then sigma v is equals to 8.5 kg meter. Then the final resultant R equal to square root of sigma h square plus sigma v square. So finally it is 23.2 kg meter. We know this is the resultant mass centrifugal force. So that is the multiplication of the mass into the radius. We know that the resultant we have find it, this is called the resultant. Resultant means the balanced mass. The balanced mass of centrifugal force of the balanced mass is 23.2 kg meter. So based on that we have to calculate. We know the value of mr is equals to 23.2, but the m value we need to find out. M equal to 23.2 by small r. The small r is already given in the question that 0.2 meter, that is 116 kg. And the position and where we have to place up the balancing mass. The position means for that we need to calculate the theta value. So tan theta is equals to sigma v by sigma h. So substitute all these values, we get it theta as 21.48. 21.48. What is the value called? The balancing mass is to be placed at theta with respect to the reference. What is the reference? That is the mass 1 only. So we have to kept the mass value in a position theta. Since the theta is the angle of resultant from the horizontal mass of 200 kg, therefore the angle of balancing mass from the horizontal mass of 200 kg, which is to be in the opposite direction. Okay, by extending in the opposite direction, that will result the balancing mass. So no need to take up the confusion that always we have to make a resultant in the both sides of the axis. That will be better for us. Okay, or otherwise by simply framing the formula as theta is equals to 180 to the given value. What is the founded value? That is 180 plus 21.48, that is 201.48. Okay, this is the method of calculating the magnitude and the position of the balancing mass for the given problem by using analytical method, means by calculation only. What is the second method? We are having with the graphical method. For the graphical method also, whatever the masses, what are the centrifugal forces we have calculated, the same thing will be used. But here also we have to draw the space diagram. But for calculating the mass and the position, here we are using the vector diagram. The vector diagram, what we are constructing here, it is based on the total angle and position of the existing masses. So now draw the vector diagram with the values of that to some suitable scale. So here we have to draw the vector diagram with the centrifugal forces. What is the centrifugal forces? M1 R1, that is 40 kg meter. So you just copy the space diagram. That means we have to draw the vector diagram based on the positions of the space diagram. The space diagram has constructed based on the question or the details given in the question. That means the angle of positioning, all the references will be in the space diagram. So according to that, we have to construct the vector diagram. Okay, then so here you just draw the firstly the mass 1, that means the position of mass 1 is horizontal. So let us take a horizontal line which is of length. The vector diagram is based on the centrifugal force. So what is the centrifugal force? He has given 40 kg meter. So with the suitable scale, draw AB, which is of horizontal, of length 40 for suitable sum scale. Here we are taking the suitable scale as 10 kg meter equal to 1 centimeter. 10 kg meter equal to 1 centimeter. Then here the diagram will be 4 centimeters. So AB is of 4 centimeter. Since the ball mass, that is 200 kg, is of length 0.2 meter, is of horizontal, then draw the AB as horizontal. Then in the continuity of the polygon diagram, the second mass is how to be presented with respect to first mass. It is of 45 degrees. So we have to continue the mass weight as second centrifugal force as 45 kg meter. So it is 4.5 centimeters. From B, draw a 4.5 centimeters inclined line. How much of inclination is 45 degrees? Then what about the from C? We have to again draw the centrifugal force as 60 kg meter, that is 6 centimeters, with respect to what is an angle, that is 120 from the reference, or otherwise from second mass line, that is BC line, it is angle of 75 degrees. So draw a CD as 125. And what is the last one? The fourth mass from D to E, which is an angle of 135 degrees with the position or distance 7.8 centimeters. So after reaching the E, we have get it AB, that is 1, BC 2, CD 3, DE 4. 4 masses are completed. Then what is the final? From E to A, we have to continue making, and the closing side of AE, that is the polygon, will represent the resultant. So by measuring this AE length will result the 2.3 centimeters, that means 23 kg meter. Here also we have to take up the scale, convert them into scale. So the final balancing mass is equal to resultant mass, but is which is presented in the opposite direction. Since the balancing mass is proportional to the MR, therefore MR is equals to how much value? 23 kg meter. Then R is 0.2, so M is equals to 11 by kg. By measuring, we can find out the total inclination of the mass from the horizontal as 200 kg, theta is equals to 201 degrees. Or otherwise, from fourth mass to the resultant, how much of angle also we can be represent here. So with that, what is the mass we have calculated and what is the angle of position we have calculated in graphical as 201 degrees and 115 kg. But what is the analytical method? The mass as 116 and angle is 201.48. So there is a small variation, or simply we can say very negligible variation. Here 1 kg of mass variation, and here it is the angle 0.48 kg, sorry, 48 degrees of variation. Then coming to the next content, the balancing of several masses rotating in the different planes. When the several masses revolving in the different planes, it may be transferred to a reference plane, that is briefly represent it as a reference plane. So RP, when several masses is revolving in different planes, they have to transform to a single plane, that is called a reference plane. So we are having here a different masses, 4 or 5 masses, all these to be cumulative positioned at one place, that is a balanced mass, or otherwise we have to kept it as a resultant mass. But for solving these number of masses individually, it is make a large time to solve it. So we are clearly observing that all these masses are come together with respect to a reference plane. So that is called the RP, which may be defined as a plane passing through a point on the axis of the rotation and perpendicular to the effect of transferring the revolving mass in one plane to a reference plane is to cause a force of magnitude equal to the centrifugal force of revolving mass to act in the reference plane, together with the couple of magnitude equal to the product of the force and the distance and the plane of rotation and the reference plane. So finally what we are calculating here, it is the individual masses will be considered or reference to the some other a line or a plane. So basically in the previous model we are considering a reference plane within the masses of rotation. But here we are taking a separate reference planes with respect to the different planes of consideration. So how to solve the problems on this, or how to calculate the balancing masses? In order to have a complete balancing of several masses in different planes, we need to consider, or we need to satisfy two conditions. One is the forces in the reference planes must be zero, that is, the resultant force must be zero, and the couples about the reference plane must balance, that is, the resultant couple must be zero. So we have to satisfy the two relation that resultant force must be zero and the resultant couples also must be a zero. Then let us consider the forces of mass, that is four masses m1, m2, m3, m4, which are revolving in the planes 1, 2, 3, 4 respectively. See, if you see in the diagram, the masses are revolving with respect to the positions with L1, L2, L3, L4, L5, and the angular positions of these masses which are showing in the figure, that is the theta 1, theta 2, theta 3, theta 4. Okay, then the magnitudes of balancing masses, that is ml and mm in the planes L and M, which is to be obtained by taking one of the planes as a reference plane. So here the magnitudes means the masses which are available at the balancing planes, that is ml and mm, that is the balancing masses. So let us consider any one of the balancing plane, that means either L or M, as the reference plane, and we have to make a notation that with respect to reference line or reference plane, the left side will be call it as negative and the right side to be call it as positive. So if you consider the M, the left side values of M are G1, L2, 3, and right side of M are 4 only. So all the values will be coming to the negative. Negative means that is not the least value, that is the direction of representation, that is the only the thing. So for clear reference we are considering L, since for the left of L as only one plane is presented, that is 1, and the right of the L is 2, 3, M4. So there is a heavy positive values will be there. So be kept that major positive values of reference will be the good thing while calculating the references or the couple values also. Then so for that I am taking the consideration as L as a reference plane. The distance between the L, since L is the reference, to all the remaining reference planes, it may be regarded as some length, and to left of the L as negative and the right of the L as positive. So the values to be chosen, and these all the things to be framed in a tabular column. The tabular column is to be of same for all the values for all the problems also. So let us consider noted down the table, that is plane, mass, radius, centrifugal force, distance from the plane L, and couple. So plane, you just write the planes, what is the position it has given in the position diagram, That means 1, L, 2, 3, M, 4. What is the same order we have to follow? That 1, L, 2, 3, M, 4, where L is the reference plane. You just mark the reference plane, which one? RP. And what is the masses? Is M1, ML, M2, M3, MM, M4. And what is the radius of rotation? R1, RL, R2, R3, RM, R4. Then what is the centrifugal force? We know that centrifugal force in the balancing of rotating masses as Mr only, simply. Since the omega is to be same for all the masses, so it is to be balanced. So MR, M1 R1, ML RL, M2 R2, M3 R3, MM RM, M4 R4. Then distance from the reference plane. What is the reference here? L. So from reference point, what is the position of one? L1 distance. So write the L1 distance, but it is presented at the left side of the reference. So we are keeping the minus L1. And second, L. L from L, what is the distance to the L? That is 0, no distance. That is the reference only. So distance from the plane of reference. So here plane of reference has capital L. So it is a 0. Then 2. 2 is kept at a distance L2 from the reference. So L2, and it is of positive side, that means right side. So we are keeping positive L2 or simply L2. In the same way L3, LM, L4. And what is the couple? Force into distance. What is the force here? Centrifugal force. And what is the distance here? Distance from the reference plane. So minus M1 R1 into L1. 0 into ML RL is 0. Next, in the same way, M2 R2 L2, M3 R3 L3, M RM MM LM, M4 R4 L4. The finally, this is the thing. Then, as a couple may be represented by a vector drawn perpendicular to the plane of couple, the couple C1 introduced by the transferring M1 to the reference plane through O is proportional to M1 R1 L1 and acting in a plane through OM1 and perpendicular to the paper. So if you see in the diagram C, couple vector, the vector representing this couple is drawn on the plane of a paper and perpendicular to the OM1 and OC1. Similarly, the vectors OC2, OC3 and OC4 are drawn perpendicular to OM2, OM3 and OM4 respectively in the plane of the paper. And the couple vectors which are discussed now are turned counterclockwise through a right angles for convenience of the diagram. The diagram of this will be seen in the D. The vectors turn to clockwise through the right angle. So all the values or all the vectors to turn into right angle, the position of the C diagram will be changed to D. And what is in the continuity, the relative positions remain be unaffected. But now the vectors OC2, OC3 and OC4 are parallel and in the same direction as OM2 and OM3, OM4. While the vector OC1 is parallel to OM1 but which are in the opposite direction. So the couple vectors are drawn radially outwards for the masses which are on one side of the reference plane and radially inwards for the masses on the other side. So in the continuity, now draw the couple diagram or couple polygon. The couple polygon which is representing in the diagram E, the D dash O dash will represent the balancing couple, since the balanced couple CM, that is the couple distance, will be proportional to the mm, rm, lm. So therefore cm is equals to mm, rm, lm. That is the vector o dash d dash, or mm is equals to vector d dash o dash by rml. From these expressions, the values of balancing masses in the plane M may be obtained, and the position of angle, that is pi, that may be drawn from the figure B. So we have to take up into the force polygon. Now draw the force polygon. The force polygon, which is showing in the figure F, the vector EO, which is in the direction of E to O, will represent the balanced force, since the balanced force is proportional to the ML and RL. Therefore, ML is equals to vector EO, and ML is equals to vector EO by RL. These equations will calculate the balancing masses of M in the plane L and the angle of inclination of alpha for the horizontal. So this is somewhat difficult to find out the values. This is a very lengthy process, but we need to solve the number of problems. We can simply calculate the relation between the vectors and the couple polygons by force and couple polygons. So with that, the session was closed. In the next class, we will discuss the problems on this model.